Welcome to ClickMyProject.com. Now we discuss about the product for 11.25 milliseconds group delay and low complexity algorithm design of 18-band Quasi-ANSI S1.111 Activa digital filter banks for hearing aids. Next we see the abstract for the product. A doctor identifies and diagnoses hearing losses through the test of pure tone audiogram and the sinusoidal signal over the active frequency from 250 Hz to 8 kHz. It's adapted to measure the patient hearing threshold and shift specific files to minimum and maximum limitations on relative attention for class 0, 1, 2 active band filters. For ordinary compensation, 1/3 active filter bank can be combined with both NAL1 and NAL2 prescription formulas. Over the past 15 years, many studies presented the various effective filter length design with different structure for digital hearing aids. Generally speaking, it's divided into two strategies. One is the uniform filtering bank and another is non-uniform filtering bank. Considerably, the natural of human auditory, the technique to dividing the frequency of uniform non-uniform is much suitable for digital hearing aids. The many non-uniform filtering bank approaches are recently divided to satisfy the needs of hearing impaired with patient audiogram results. This paper presents a novel algorithm on architecture design for 18-band Quasi Class 2 and Shift S1.11 1/3 active filter bank. This proposed design has several advantages such as the lower group delay, lower computational complexity and lower matching error. This technique we developed in this paper can be summarized as follows: as a simple low-pass filter and the discrete cosine transform modulation are utilized to generate the uniform 9-bank filter bank first, and then all the elements of z⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻ filter bank to obtain a non-uniform filter bank. A few recursive structure and variable length algorithm is further developed to efficiently accomplish the DCT modulation. Thus, the spectrum of LPF can be easily spanned and flexibly extended the location of desired central frequency. After employing the multi-rate algorithm, an 18-band non-uniform filtering bank is generated from the two 9-band subfilter bank by following the proposed design step and parameter determinations. Compared with the latest Quasi Class 2 and Shift S1.11 design, the proposed method has totally the 72.8% reduction of multiplication as per sample, 11.25 millisecond group delay and 949 addition discrete per sample. Moreover, the maximum matching error the proposed two method is averagely equal to 1.7 dp, much smaller than that the lower design. For the proposed variable length DCT modulation, only 2 adders, 2 multipliers, 2 multiplexers and 5 registers are required for the hardware implementation of after applying the VLSI retiming scheme. Overall, the proposed filter bank design new solution to further improve the application of overall architecture. This is the final design for our overall process. Next, we see the flow diagram for the product. First, we given the any1 speech signal to be browsed using the M file code. Then to apply the pre-processing for module the noise addition. This noise for AWJ noise for real-time noise to be added in the original input speech signal, and to apply the noisy signal into the simulink design. This simulink design to be considered the 3 stages based designs are implemented: signal decomposition and the threshold function signal reconstruction. The signal decomposition process to be split into the signal into low and high and using the downsamples, and the threshold functions to set the threshold level for the 0 and 1 to -1 positions, and the signal reconstruct to add the signal and to be reconstruct for and given to finalize structure for the original information for overall simulink design. This simulink design based on our DWD based architecture for a modified transformation architecture. This architecture to reduce the overall congestion. These bands are applied to the 18 band limitation for overall simulink based design. This simulink based design each and every time to be split in the band by level and to add the level by level for reconstruction stage. Then to use the system generator function. The system generator function is used to process the Xilinx oriented block into in the signal or image based works. We develop the signal based work signal filtering function using the digital filtering banks and apply the digital components for overall digital filtering bank design. Then we design and run the overall output and to remove the noise removing for the overall simulink based design and to identify the noise removing part. Then the system generator is to convert the Xilinx software using to VHDL code generating process. The VHDL code to be simulate and synthesis the using the Xilinx oriented process, and we analysis the hardware requirement of overall our required design a digital filtering band 18 band level design. This is the flow diagram for the overall product. These designs are applied to the MATLAB works, and these three works are applied to the simulation work, and these three works are applied to the Xilinx works. This is the final process. Next, we see the final output for the product. This is the main file for to generate the select any one of the speech signal and to add the noise and to split the certain limitation for overall speech signal and to apply the simulink designs and directly open to the our simulink design. Then to run the our coding for the selected noise sequence. This is selected input signal. Then to open and to run the overall speech signal. This is the limited input signal and to add the noise signal. This is the simulink design for our overall process. This is the noise input signal to be applied over the simulink design. Then to run the our simulink design, this design consists of 18 band for the overall digital filter bank architecture. These subsystems are considered the low pass decomposition, high pass decomposition, and the reconstruction stage for overall addition process. Then to run this simulink design and to generate the noiseless signal for overall given input speech signal. These simulink designs are mainly specified about the FPGA based blocks to be presented in our overall Xilinx based block. The simulation was completed successfully. Then to run the overall block for our required denoise architecture using the digital filter band design. So the closing window for our overall architecture. Then to close our noisy signal. Then to speech the this is the final output for the given input signal. This is the final simulation window for the noisy signal, and this is the given input speech signal in the analog waveform, and this is the noise addition for to differentiate amplitude for the noise addition speech signal. So non-uniform noise to be presented in our given input speech signal. This is the removed final output denoised digital signal for digital based process. This is the given output digital signal for final simulink design. This is the noise removing part for the our overall process. This is the design for our process. Then to open the simulink based system generator design used to generate the our coding for the Q design to the Xilinx oriented process. Finally, this is our the VHDL code designs for our required denoise filter architecture. This is the digital filter bank. This is the digital filter bank code for using the system generator and convert the VHDL code and to generate our overall design based process and to analyze the all report things for the our required filtering bank architecture. So device utilization summary. This is the timing summary for overall architecture process. This is the final process for digital filter bank architecture design.